Welcome. Today's notes worksheet is entitled Applications of Polynomial Functions and Equations. This lesson is a great opportunity for us to do a comprehensive review on all the characteristics of the zeros of polynomial functions, and then maybe extend a little bit into a couple applications as well. So why don't we start it out with example 1 at the top. I have a fairly large degree polynomial, and you can see all of the characteristics run down on your notes worksheet here. We'll go through them obviously piece by piece. So example 1 states, use the function f of x equals x to the 6th plus 5x to the 4th plus 2x squared minus 8. So degree 6 polynomial. That's great. Kind of up in the ante a little bit here. And let's start with the very top. So number of complex zeros, pretty straightforward. This is in standard form, of course, so all we need to do is kind of go out in front there and take a look at its degree. And it looks like this is a degree 6 polynomial. So as a result, we should be getting 6 zeros for this particular function. Now the composition of those zeros is to be determined, but at this stage we should be able to find 6. So let's go ahead and get the pieces together in order to find the 6. Let's kind of talk about what that would mean in terms of real zeros versus imaginary zeros. What are the possible combinations of those two? And so let's kind of start it out with the real zeros right up here. What we concluded in previous lessons is that potentially all of the zeros could be real. So if there are 6 complex zeros, maybe all 6 of them are real. Now the question I guess I have for you is, could 5 of them be real? That's to me kind of the key for this particular spot right here. Could 5 of them be real? Well, remember what that means, of course. If 5 are real, then 1 would be imaginary. And is it possible to have 1 imaginary zero for this particular polynomial function with all real number coefficients? And no. As we all know, imaginary zeros, show up in pairs. And so as a result, not going to happen. So can't be 5, but could be 4. Because then that would mean 4 real, 2 imaginary, and again that would have them showing up as a pair. And then hopefully you can play out the rest. That means then that 2 of them could be real and 4 imaginary, or potentially none of them are real and all 6 of them are imaginary. So just make sure we have our reals and zeros adding up appropriately. And so in this case, here are our pairs. Get no pairs, or 1 pair, or 2 pair, or 3 pair of imaginary zeros. And so those are the 4 possible combinations, real and imaginary, that we'll be looking for here. It's one of these 4. It's either 6, 0, 4, 2, 2, 4, or 0, 6. No other ways that this can play out. All right, super. Well, let's go get the next piece right here. As soon as we talk positive real zeros and negative real zeros, we're certainly looking at Descartes' rule of signs for this. So I might do a little work off to the side here. Feel free to do your work wherever you'd like, of course. But let's see what we have going on. Possible positive real zeros, Descartes' rule of signs. All we're looking for is going right to the function, and let's talk about sign changes here. So as I look for sign changes, positive 1 to positive 5, nope, no sign change. Positive 5 to positive 2, no sign change. Positive 2 to negative 8, there is a sign change. So it looks like 1 sign change right here. And as a result, Descartes would be pretty definitive for this particular function. We should be finding 1 positive real zero. No doubt about that one. All right, great. Now before we can get into the idea of possible negative real zeros, we need to do a little algebraic manipulation on this. So let's do our little f of negative x here. And let's see what I have, of course. So this would be replacing x with negative 1x, essentially. I'm curious if you happen to see something based on the exponents in this particular polynomial. Maybe you do at this stage, maybe not, but we'll figure it out one way or the other. So that's what I'm looking for. And then think about this for a second. As I go ahead and simplify each of those 3 pieces, think of this as a negative 1 times x raised to the 6th. Negative 1 times x raised to the 4th. Negative 1 times x raised to the 2nd. Well, what happens when I take negative 1 and raise it to the 6th? It becomes 1. And so as a result here, I'm hoping you're seeing this, and we've kind of talked briefly about this before. This just reverts to 1x to the 6th. This one will be 1x to the 4th because negative 1 to the 4th is 1. and then obviously times the 5. So long story short here, it does not look like our sign changes at all based on the fact that each of these exponents is even. That looks great. So, it's the same thing. We already did the sign changes on it, so let's just run it through one more time. No sign change, no sign change. There's one sign change right here. So that's the one we're focused on. And so again, in this particular function, extremely definitive. No ambiguity whatsoever, no ors as we go through Descartes' rule of signs. It's literally one positive real zero and one negative real zero, which means there are two real zeros for this particular function. That's the only way this can play out. So there are two reals, which means the other four have to be imaginary. We'll be looking for that. All right, that's great. Next piece of business is to go into the possible rational zeros right there. So let's go ahead and just do our P over Q as soon as you see that phrasing. So it's just P over Q. And this one's really not too bad, but I'll just do a quick review on it. P would be all the factors of -8. So we're looking at plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Q, all the factors, of course, of the leading coefficient, which is just 1, and I'm seeing a plus or minus 1 on that. That's looking pretty good. If I was to do all my combinations, hoping you kind of see this without a whole lot of hoopla here, but 1 over 1, 2 over 1, 4 over 1, and 8 over 1. And so there are exactly 1, 2, 3, 4, 5, 6, 7, 8 possibilities for zeros of this function that are rational in nature. All right, well, let's put those in play. Now, if we did not have a graphing calculator, we would just kind of start our process with synthetic division on, one of these and hope for the best. And if it didn't work, we'd try another one and so forth. There are two real zeros. We'll see, hopefully, that these two are rational. If they're irrational, not sure where it'll head. But for right now, we're just going to use our graphing calculator to get us going. Now, I'm going to do just a touch of erasing really fast here just because I'm going to need room to do my synthetic division. You can put this wherever you'd like, but I'm going to need some room to do some synthetic on this. Okay. Well, everybody, let's bring up the calculator. Let's go get these 6 zeros. Let's see what we can do with it. So calculator is ready to go. There we go. And go to your y equals if you would, please. And let's type in the function. So x to the 6th. And I do have my 5x to the 4th, of course. And plus the 2x squared. And last but not least, how about we go minus 8? Zoom standard should, of course, suffice. So zoom in number 6. And we have our nice degree 6 polynomial function graphed on the coordinate plane. Notice, of course, it's degree 6 with a positive leading coefficient. So rise, and behavior, we've seen that. We have our one turning point down here. And notice we do have our two real zeros right here, one on the positive side, one on the negative side. So certainly Descartes was right on that piece. And let's go ahead and try to get what that is. Now, I'm assuming this is 1 and -1. Those are on our lists, and it looks really like that's going to be the case. Remember, you are always more than welcome to just do zoom trace and go ahead and just do a left bound and a right bound and so forth if you'd like. Totally your call. But notice that's going to be 1. And again, I won't waste our time on this. I do know that that's -1 over there. So it looks like we have at least 2 to work with, and then we'll have to decide what to do from there. So -1 as the 1 negative, +1 as the 1 positive, and then we'll have to go get the 4 imaginaries. Okay, well, let's go start this out. Let's break this polynomial function right on down. So I'm going to start with +1. I like doing that. Now, one thing, obviously, with this one, hope it sort of got your attention immediately. We're going to need lots of placeholders, so don't forget those, please. If nothing else, this problem is a good reminder of that piece. So I've got 1, 0, 5, 0, 2, and 0, -8. All right, looks good. Let's be quick. Let's just make sure everything is legitimate there. Bring down that 1, and let's go get them, everybody. Okay, looking good. Throw my curtain in there to break off the remainder. And obviously the remainder is 0, and we knew that would be the case. So 1 is a 0 of this function, no doubt about that. We broke this down. X minus 1 goes into the degree 6 this many times, and this is our quintic polynomial. So now what we want to do is see about x plus 1 going into it. So let's use our c value here, which would be -1, and let's go a little further. So degree 6, degree 5, let's get down to degree 4. All right, so hopefully the whole process is really making pretty good sense. Let's just make sure it plays out the way we want it to. Got that. There we go. All right, looking really nice. So we have degree 6, degree 5, degree 4. And so at this stage, and it's up to you what you want to do with this, I'm just going to write out what we have this function equivalent to at this point. One of the factors is x minus 1, producing a 0 of 1. One of the factors is x plus 1, producing a 0 of -1. And those two together go into that degree 6 polynomial this many times, x to the 4th and 6x squared and plus 8. So that's what we have at this stage. And you know, at this point in time, I don't really have the calculator to do any more work with this. It's going to be up to me to take more traditional roots in order to break that quartic function right on down. So let's deal with that piece. We have our zeros from these two guys, so let's get the other 4 from these two right over here. So I have this in action. I'm going to set that to 0. And do you see it really has a nice quadratic feel to it, even though it's not quadratic, but it's got that trinomial feel where I maybe, just maybe, can go ahead and factor it with two binomials. Instead of x and x multiplying to that, it looks like x squared and x squared. And that'll be great because our outside and inside will combine to an x squared, which is perfect. So I think we're ready to roll. I think I just need two numbers that multiply to 8 and add to 6. And so how does this sound right here in terms of the factored form of that quartic? So again, as you can kind of see, I have that factor and that factor, this quadratic factor, this quadratic factor. These two are definitely prime in the real number system. So what we'll do is just go ahead and solve them independently here and get our imaginaries out of it. But x squared plus 4 equals 0, and x squared plus 2 equals 0. It looks great. Hoping you all see this piece unfold. X squared equals -4, and so x equals plus or minus 2i from those two right there. That's great. And in this case, okay, so x squared equals -2, and undo the square in this case, and it looks like plus or minus, hoping you see it as an I root 2 on that. Square root of -2, pull out the I and the root 2, of course. So we have, when all is said and done, 1, 2, 3, 4, 5, 6. Perfect. Everything played out consistently there, so let's get that in play. I'm going to do it as a plus or minus 1, plus or minus 2i, and plus or minus I root 2. All right, good start. Looks nice. Let's go on to the next piece. So what we're going to do is just kind of set up a couple of polynomial equations here. And the good news is we're going to let the graphing calculator do most of the work on this. So just some strategies. You can take it for what it's worth, as always. But just some ideas to think about as you read some of these problems and try to figure out what's going on. So number one, first and foremost, you have to set up a polynomial equation from the information in the problem. Easier said than done, of course. We'll just take it piece by piece. Number two is kind of the big thing in my opinion. So put a little asterisk, if you would, next to that. This whole unit is talking about zeros of these polynomial functions. So right away, guys, let's set it to 0. Now here's the beauty of it. I bolded it for you, but let's underline it as well. Don't try to be fancy here. Don't simplify when it's not necessary. All we have to do is set it to 0, because what we're going to allow to happen is the calculator is going to solve what we need. All right, so it's not necessary to simplify the equation. And what we're going to do, though, once we have it set to 0, we're going to think of it as a function. So graph it as a function on the calculator and find the real zeros. And of course, real zeros show up as x-intercepts. So we just want to figure out the x-intercepts that make sense with this problem. Do we care about imaginary answers for these types of problems? Absolutely not. So again, we're not breaking down, we're not doing synthetic division, we're just letting the calculator do its work, and we're interpreting what we need from there. So let's give it a try. Examples 2 and 3, just to at least get a little experience with this, and then you'll try, obviously, a few on your own. So example 2. We've definitely seen this scenario before in a couple different contexts, so let's try it one more time with this. An open box is to be made from a rectangular piece of sheet metal, 15 inches by 9 inches, by cutting squares from the corners, turning up the sides. Let x be the length of the sides of the squares removed. Find x, so the volume of the box is 56 cubic inches. All right, you don't have to underline that, but I'm going to put that there. So we've done these problems where I think we've done domain and range with this type of scenario. We've done maximizing with this type of scenario. Now what we're going to do is solve it as just a single equation. All right, volume is 56 cubic inches. And then we'll take one more step, determine the dimensions of the box. Okay, great. So here's the situation, just in case you've forgotten how this plays out. We just have our rectangle right there. Let's label it 15 and then 9. Looks great. We're going to cut out those corners, of course. There are an infinite ways, a number of ways to cut those out. Just going to kind of draw it like this for our purposes. And that's our x by x. Sounds good. And hopefully you can kind of picture what happens when I cut those out. I get a figure that looks something like this. Again, I can't really draw very well, but hopefully you get the idea. Flaps fold up, and we're ready to go to create our open top box. Now, we've seen this before. Obviously, the volume of a box is just length times width times height. Now I'm going to deal with the length, width, and height, of course, since we've dealt with that before. The length of the box was 15, but we took away x from each of the corners here, so I took away that x and that x to get this length. So 15 minus 2x. The width, of course, again, we've seen this scenario before. The width of the box will be from there to there. It was 9 at one point in time, but we took out x from here and x from here, so taking away 2 x's. And last but not least, the height of the box. Remember, we're folding up that flap, so the height of the box essentially is that piece right there. And that, by definition, is x. That's great. Now, what we've done before with this is treat this as just a volume function. And we've looked at the infinite number of possibilities. And in fact, there's one way to optimize it there and to create the best volume, the maximum volume. But in this case, instead of trying to maximize it, I want a specific numerical value for the volume, 56. So that's what goes in here. And now notice we've got an equation in one variable. If I was to simplify this, and I'm not going to, this would be cubic. So it is definitely a cubic polynomial equation. What I'm going to do is just set it to 0. So watch how nice this is. I have 15 minus 2x, 9 minus 2x, times the x. All I did was bring over the 56. Again, there is no reason to multiply all this out and combine with the minus 56. You don't need to put it in standard form because we're not going to do any synthetic division on it. All we are going to do is put it in the graphing calculator at this stage and see what we get as our values. So let's go give them a try. Go to the y equals if you would. Clear that first one out. And exactly as I wrote it up on my board here, that's how I'm going to type it in. So 15 minus 2x, 9 minus 2x, times the height, which is x, and I'm just going to throw the minus 56 on the back end. Now, a couple ways we can kind of set up our window. You can zoom standard and kind of hope for the best here, but I don't know, ultimately, think about what we're looking for here. Do we care about any negative x-intercepts? Would it make sense at all for x to be negative? No, not in the least bit. So you can leave this if you want. I will leave that up to you, but I'm going to start at 0. obviously, guys, we can't cut out too much here. This is a relatively small situation that we're dealing with. So I'm going to keep it at 10. And I don't even care about the y's. As long as I can see the x-intercept, which would be a y value of 0, I think we're good to go. So negative 10 to 10, I don't know, I could probably tweak it, but there's no real need. Long story short, let's graph it. And notice what we end up getting here. I end up getting 3 values where it hits the x-intercept. 1, 2, 3, all of them positive. So what we would do at this stage, of course, is second and trace, go to our calculate menu, and get the zeros here. Now I'm going to do probably 1 at least, maybe 2, we'll see. But ultimately these should be good numbers. You know how to do this already, so I don't want to belabor the point. Let's see, where the heck are we? Here we go. I'm going to go ahead and get that first one. Let's see if I can find out where we are there. There we go. All right, so I'm to the left of it. That took some time, but we got it. Let's go to the right of it, and let's hit enter one more time, and that looks great. All right, so one of the x values is 1/2. That's perfect. By the way, just again, I think to save ourselves a little time and energy, this value right here happens to be 3.5. You're more than welcome to do a little left bound and right bound on it, but you'll get 3.5 on that piece. This one right here, perfectly on our tick mark, and I believe that is 8 when all said and done. So again, if you don't believe me, feel free, go ahead and get the zeros on that, but it looks like 0.5, 3.5, and 8 would be our x values. So that is exactly what I'm going to write in here. So we did, as I said, this is cubic, so we should expect 3 answers to this particular equation. It just so happens all 3 are positive real numbers. So I got 0.5, I got 3.5, and I got 8. And that looks really nice. I'm going to throw one curveball at you, though. In terms of the x values, and of course what we want to do is do this last piece in just a second, determine the dimensions of the box. Here's what I would say to you. 2 of these answers are great. They're going to give us exactly what we need as we do the last step. One of those answers is actually, it's not feasible for our situation here, and we need to get rid of it. So I guess I would ask you, which of the 3 here, and this doesn't always happen, by the way, but you'll just have to use your discretion on this, which one of these is not legitimate? Well, if you look at the problem, I think we have an issue with this number right here. Can I have an x value of 8 in this particular situation right here? Can I cut out 8 from here and 8 from here if the whole entire thing is only 9? No, of course not. So this value, even though it makes the equation true, it simply does not make sense within the context of the problem. Okay, I cannot cut out 8 from each corner here. I don't have enough box to do that. Okay, so now we have what we need. I think this one works. I think we can get a nice length, width, and height out of this x value, and I also think we can get a nice length, width, and height out of that value. So if you're wondering how to get the dimensions, remember these are your x's. That's the length, that's the width, and that's the height. That's what I'm looking for. It's all in terms of our x that we just found. So I'm going to do the first one and then probably just write the second one, but essentially it's 15 minus 2 times 0.5. That'll be the length. The width would be 9 minus 2 times 0.5. And then obviously the height is going to be 0.5. So that'll be our length, width, and height in just a second. And then I would repeat the process with 3.5. So I would do that piece right there. And 9 minus 2 times 3.5. And then obviously 3.5. So when we do these calculations, again, trying to make a long story short here, if at all possible, this would be a length of 14. This would be a width of 8. And this obviously would be a height of 1/2. So let's go ahead and write that down here. So length, width, and height, I'm going to do that. 14 by 8 by 0.5. And by the way, guys, if you were to multiply 14 times 8 times 0.5, what would you get as your volume? absolutely 56. Great. If I repeat that process on this end right here, it looks like I would get 8 for the length. Looks like I would get 2 for the width. And it looks like obviously I'd get 3.5 for the height. If I multiplied 8 times 2 times 3.5, would I also get my magic number of 56 for that volume? Of course. Do you see, by the way, if I tried to put the 8 back in, do you see that I would end up getting like a negative length and a negative width? And that wouldn't make sense, of course. So that's why we got rid of that one. So checking the answers just to make sure it makes good sense. They're all positive, so we knew they were at least feasible. It just so happens this one did not work. All right, cool. So that's how it's going to play out. Notice no synthetic division, didn't talk about any of the characteristics. All I did was set up an equation, let the graphing calculator do its work, and then interpret from there. Okay, let's try example 3. It says, what is the length of the edge of a cube if, after a slice 1 inch thick is cut from one side, the remaining volume is 294 cubic inches? All right, not too bad. So let's see what we have going on here. So I've got the length of a cube. So let's just draw a cube, I guess. Half the battle is just getting a visual picture and labeling it and seeing what information we can come up with from there. So I have a cube. And we're looking for the length of the edge of the cube. So, essentially x by x by x. That'll be that piece right there. And then here's kind of the scenario. And if it doesn't sound right, that's okay. I'll try to interpret as best I can up here. It says, after a slice 1 inch thick is cut from one side. So we're going to take one side here, and I'm literally just going to take my slicer and cut into it. So here's what it's going to look like. I'm going to draw this as best I can. For me, that's a challenge, but I'm going to go ahead and slice it right there. See if you can picture this three-dimensionally. So does everyone kind of see that? I'm going to take out 1 inch thick slice from that left side right there. So that is going to go. Try to picture that piece if you can. And then the remaining volume, after I have sliced that out, is going to be 294 cubic inches. So again, just one more time, literally took my slicer and cut out from that left-hand side right there. I cut out exactly 1 inch, so from here to here is an inch, and remaining volume. Well, again, just kind of getting myself thinking. It's just coincidence that I put these two, but we are talking about a rectangular prism at this stage, and volume is length times width times height, as it was in the last problem. So my volume is 294. Now, it depends what you want to kind of think of as in terms of length, width, and height, but I guess I'm just going to think of the length now from here to here. So remember, I had a cube where all of the dimensions are the same, and that is my variable. So it was x. Now I took out, at least from the length, and that's where I did my slice, it looks like I took out an inch, so it seems to be this is going to be x minus 1. So from here to here is x minus 1. Okay, to me that's sort of the big thing, because then I didn't really touch the dimension on the width here. This is going to be the same. The height is still going to be the same. It was coming from this end, so I only affected the length. So I have x minus 1 times x, and that looks great. I mean, this is actually an equation that I can probably simplify pretty quickly without risking too many mistakes, but I'm going to leave it just to verify the point. It's not necessary to do any simplifying. Again, if you want to, especially here, x times x is easily x squared, and you could probably distribute that in without any issues whatsoever. But I'm going to leave it like that, just to have our equation set as we initially did it, and then now just setting it to 0, so I'm just subtracting the 294. All right, so let's go ahead and get our x value, which is exactly what we're looking for here, so that's kind of nice. So let's go back to that y equals one more time, and I have x minus 1, and then x. Again, it seems kind of silly not to at least do x squared on that, but that's all right. Minus the 294. Again, same deal. Do I care about imaginary zeros for this cubic? No. Do I care about negative real zeros for this cubic? No. All I care about are the positive ones. So, I'm just going to keep that window and hope for the best. If I need to increase my maximum here, maybe 0 to 10 is not sufficient. Maybe I'd go 0 to 20 or something like that. All I could say is, see what you can find. Okay. So it looks like the value worked out nicely. 1, 2, 3, 4, 5, 6, and it looks like right on the 7 there. If you want to go ahead and do a left bound, right bound on that, you're more than welcome to. I'm just going to call it 7, and that's looking pretty good. So we've got an x value of 7. Don't care about the other two. Other two didn't show up really where I needed. I mean, the one thing I guess I would maybe, just maybe, be concerned about is, did it show up anywhere else past 10? And, in this particular case, I went out to 50 and nothing showed up. If you're still not convinced, you're more than welcome to go out even further. But ultimately, nothing seems to be showing up there. So, oops, I went up to 1,000. I meant to go up to 100. So, just right there, that seems to be the only one. If there was a negative one, don't care. If this is the only real zero and the others are imaginary, irrelevant. That's the only one I need. Okay, so let's see what we were looking for initially with the problem. What is the length of the edge of a cube? So it looks like just 7 inches. So it's 7 by 7 by 6 at this stage. And it really wasn't asking for the full dimensions of our new figure, but just 7 inches on the length of the cube. All right, so again, just make sure you set up your equations. As soon as you set the equation up, just get that to 0. Get it in the calculator, get your value that you want, and then interpret what that means just based on what the question was asking. Here, just the length of the edge of the cube. All righty. Let me know if you have any questions on this particular lesson or anything else as we start to bring this unit to a close. Thanks.